Acids and bases test answers. Question 1. Write an expression for the dissociation constant Ka of propanoic acid. Okay, so if you want to write an expression for Ka is going to be equal to H plus times A minus. Now A minus in this case is going to be all of this. And then we want to divide it by the concentration of the acid. Write an expression for pKa in terms of Ka. Well, pKa is the same as pH. So pKa is going to equal minus log to the base 10. Instead of the hydrogen ion, it's Ka. So like pH is of the hydrogen ion concentration, pKa is of Ka. Calculate the pH of a 0.1 solution of propanoic acid, given that Ka equals 1.35 times 10 to the minus 5 moles per decimetre cubed for this acid at 25 degrees C. We're working out the pH of a pure acid. We can use the approximation where Ka is equal to the hydrogen ion concentration squared divided by Ha. Okay, we want the hydrogen ion concentration, so that's going to be equal to the square root of Ka times the original acid concentration. We know Ka is 1.35 times 10 to the minus 5, and the concentration is 0.1. And if we calculate that, we should get 1.16 times 10 to the minus 3. That's the hydrogen ion concentration. So now to find out the pH, we put it into our usual pH equals minus log to the base 10 of the hydrogen ion concentration. And that should give you a pH of 2.93. Make sure all pH values, unless otherwise stated, are written to 2 decimal places. In terms of how the marks are awarded for that, you get 1 mark for showing this arrangement. It says in the mark scheme that this bottom bit really should be the propanoic acid, but I don't think they're going to be too strict about that. You get the 2nd mark for identifying that 0.1 is the concentration of the propanoic acid. To be honest, if it's shown in the calculation correctly, I would award that. You get the 3rd mark for working out the hydrogen ion concentration. And 1, 2, 3, 4. You get the final mark for working out the pH, which should be to 2 decimal places. And obviously 1 for that bit and 1 for that bit as well. Right, this next bit asks you to explain why an aqueous solution containing propanoic acid and its sodium salt, so we know it's a buffer, constitutes a buffer system able to minimise the effects of hydrogen ions added. So you need to explain what's going on. So the first thing you would say is the concentration of the salt, or the anion from the salt, is high. And that's important, there's a really high concentration of that. If you add a small amount of H+, the H+ will react with the CH3, CH2, COO-, and the position of equilibrium of the acid can change to accommodate that. So a slight increase in the concentration of the acid is not going to have a huge effect on the ratio Remember for this that the pH is directly proportional to that ratio. So as long as you're not making a huge change to that, now in this case, that one would go down a tiny bit, that one would go up a tiny bit, but they both are in large excesses. So adding a small amount of acid and this one going down a little bit and this one going up a little bit isn't really going to change that ratio by very much. If that ratio doesn't change by very much, the pH won't change. Write an equation for the reaction which occurs when the weak acid HA is added to water. So we're going to add this to water, and it is to some extent a reversible reaction. It's going to split up into its ions, which are now in solution. So make sure you put those aqueous signs in. Write an expression for the dissociation constant Ka of the weak acid. So Ka is equal to the concentration of the hydrogen ions times the concentration of the A- ions over the concentration of the acid. The dissociation of HA is an endothermic process. So that means it's going to be endothermic in the forward direction, exothermic in the backwards direction. Deduce the effect, if any, of an increase in temperature on the value of the dissociation constant. So if we increase the temperature, the reaction is going to go in the endothermic process, so it's going to go forwards. So we're going to get an increase in the amount of HA and A- and a decrease in the amount of this. So this bit will increase, this bit will decrease. The top increases and the bottom decreases, we'll get an increase in the value of Ka. An increase in the temperature on the pH of an aqueous solution. So what effect is going to happen to the pH? Well, again, we know if you increase the temperature, it's going to move in the endothermic direction, so the amount of H+ ions are going to increase. It's going to become more acidic. If the hydrogen ions increase, the pH is going to have a lower value, so that's going to decrease. An increase in the concentration of the acid on the value of Ka. Well, if you increase the concentration of acid, the equilibrium position will shift until it reaches the same position of equilibrium, so it will have no effect. Changing the pressure would have no effect as well. Like if you think back to the Kc, when you increase the concentration or the pressure, it has no effect on the value of Kc. The only thing that affects Kc, Kw, Ka, all of the Ks that we come across is changing the temperature. So this particular one will have no effect. Identify a compound which could be added to aqueous ethanoic acid so that the pH of the resulting solution would not change significantly if a small volume of dilute hydrochloric acid were added. State the name given to solutions which behave in this way. So we want to make a buffer solution. So we either want the salt of ethanoic acid, which would be sodium ethanoate, or we can make the salt by neutralising a little bit of the ethanoic acid. So any base would be suitable for that. So something like sodium hydroxide would work as well, as long as it wasn't in excess. And the name of the substance we're forming is a buffer. At 25 degrees C, the constant Kw has the value 1 times 10 to the minus 14 moles squared decimeters to the minus 6. Define the term Kw. So when you're asked to define any of these, you just write the equation. We then need to define the term pH. If you do get one of these questions, it's a lucky question to get because it's an easy way to pick up a couple of marks. We then need to calculate the pH at 25 degrees C of a 2 molar hydrochloric acid solution. So you're just going to put the number straight into the equation. This really is quite an easy question. And don't be thrown if you get a small negative number for a strong acid. That is okay. Right, to calculate the pH at 25 degrees C of a 2.5 molar concentration of sodium hydroxide. So we're going to use Kw. And we're going to work out the hydrogen ion concentration, which will be Kw, which has been given to you in the question, divided by the concentration of the base, we then want to work out pH, which gives us a pH of 14.40. Again, always to 2 decimal places. So you get 1 mark for doing that bit and 1 mark for working the pH out. Look at them with some common sense as well. It's a strong solution of sodium hydroxide. A pH of 14.4 sounds reasonable. If you've got a pH of 3, you know you've made a mistake. Calculate the pH at 25 degrees C of the solution that results from mixing 19 centimetres cubed of 2 molar HCl with 16 centimetres cubed of 2.5 molar sodium hydroxide. So the first place to start is to work out the moles of H+. Now it's hydrochloric acid, so 1 mole of hydrochloric acid gives you 1 mole of hydrogen ions. So we'll do a vol times conc. And we need to work out the moles of OH-. Again, it's 1 to 1, so every mole of sodium hydroxide is going to give you 1 mole of hydroxide ions. So if we have a look at those two, then the hydroxide ions are in excess. So the next thing to do is to work out the excess hydroxide moles, which will be 0.04 minus 0.038. So it's 0.002. Then we want to work out the concentration of the hydroxide ions. So that's going to be moles divided by volume, and the total volume is going to be 19 plus 16 added together. So that's going to give us a total volume of 35. So that's a new concentration of 0.0571. Okay, now we've got the concentration of the hydroxide ions, we can use Kw to work out the hydrogen ion concentration. We've got Kw, we know this is still at 25 degrees C, so we've got Kw from the previous question. And we've just worked out the new concentration of the hydroxide ions. Then to work out the pH, we're going to use minus log to the base 10 of the hydrogen ion concentration, which will give us a pH of 12.76. In terms of how the marks are allocated, you obviously get a mark for the final answer. You must show all of your workings to get the rest of the marks though. You get 1 mark for this bit. This is out of 6. You get 1 mark for both of these together. You get another mark for working out the total volume, and another mark for working out the excess moles of hydroxide ions. The sketch below shows the change in pH when a 2 molar solution of sodium hydroxide is added from a burette to 25 centimetres cubed of a 0.15 molar solution of the weak acid HA. Okay, so we know that these are going to react in a one-to-one way. So at the point it's neutral, the moles of sodium hydroxide would equal the moles of acid. So the moles of HA are going to be 25 times 0.15 divided by 1,000, which is 3.75 times 10 to the minus 3. That's going to be equal to the moles of sodium hydroxide. So the volume of sodium hydroxide is going to be equal to the moles divided by the concentration times 1,000 . And the concentration was 0.2. And that gives an answer of 18.75 centimetres cubed. This is a titra, so it should be recorded to 2 decimal places, as all titras always are. You get 1 mark for working out the moles of acid, and you get a 2nd mark for getting the volume correct. What is significant about the part of the graph labelled B? So we're looking here. So we know X is the equivalence point. That's when the amount of acid is equal to the amount of alkali. So X over 2 is the half equivalence point, and B would be the pH at half equivalence. So the first thing is, it is the pH at half equivalence, or half neutralisation. That gets you 1 mark. Second thing you need to know, at half equivalence, pH is equal to pKa. And that is how you work out the Ka of a weak acid. The pH equivalence for C, well, we know it's a weak acid and a strong base. So if it's a weak acid and a strong base, then the equivalence point is going to be between 7 and 11. So we want a value that's greater than 7, but less than 11. So any number between those two. So if you've got between 8 and 10, you've got it right. Identify a suitable indicator. So if we end up with our equivalence up here, then we want an indicator that changes colour up here. Phenolphthalein would be the ideal one. If we've got a strong acid and a weak base, then we'd want one that changed down here, which is methyl orange. Both phenolphthalein and methyl orange would both be fine if it was a strong acid, strong base. If you spelt phenolphthalein wrong, learn how to spell it. So it's phenol, as in an OH joined to a benzene ring. Phthalene, this is the bit that's slightly trickier. If you make a small mistake on it, I don't think they're going to penalise you, but really you should have phenol at the beginning. If you haven't got that, then that's quite a long way away from the actual answer. And just to clarify, this section was out of 7, not 5. A 0.210 mole per decimetre cubed solution of potassium hydroxide was added from a burette to 25 centimetres cubed of a 0.16 molar solution of ethanoic acid in a flask. Given that the value of the acid dissociation constant Ka for ethanoic acid is 1.74 times 10 to the minus 5 moles per decimetre cubed, calculate the pH at 25 degrees C of the solution in the conical flask at 3 following points: before any potassium hydroxide is added, after 8 centimetres cubed of potassium hydroxide solution has been added, after 40 centimetres cubed of potassium hydroxide has been added. Okay, so let's break this one down into A, B, C. Okay, so the first one, I'm just looking at an acid that's in the solution. So we know that the value of Ka when it's just a weak acid can be approximated to this. So if I want to work out my hydrogen ion concentration, it's going to be the square root of Ka times the original acid's concentration. So in this case, Ka is 1.74 times 10 to the minus 5, and the concentration of the acid is 0.160. So the answer to that would be 1.67 times 10 to the minus 3. So its pH would be 2.78. Again, remembering pH to be to 2 decimal places. Now in this one, you would get 1 mark for showing that it abbreviates down to that. You would get a 2nd mark for working out this, a 3rd mark for working out this. And if I look carefully at the mark scheme, it wanted you to state Ka to start with before you simplified it and made the assumptions. Okay, and that would get you the 4th mark. If it is a long question like this and you haven't had to state Ka, it's worth defining Ka first before you use any abbreviations. Right, for part B, we've had some sodium hydroxide added, which means some of the acid has been neutralised. And when we add the potassium hydroxide, then we're going to get the formation of a salt. And if we get a formation of a salt, we know we're going to end up with a buffer question. So the first thing to do is to work out how many moles of acid we started with. Okay, and then we want to know how many moles of hydroxide ion we added. And we know we've added 8, and the concentration is 0.21. Okay, so we know the moles of acid that are left over are going to be what we started with minus any hydroxide that we added, which is going to be 2.32 times 10 to the minus 3. And the other thing we want to know is how many moles of our salt we're going to be made. Now, every 1 mole of potassium hydroxide is going to make 1 mole of our salt. So that is just going to equal 1.68 times 10 to the minus 3. Okay, we also need to know the total volume this is in, because both of these need converting back into concentrations. Now we're going to use the expression of Ka to be able to work out the hydrogen ion concentration. So it's going to be Ka times the original acid's concentration divided by A minus. Save a little bit of time here because the volumes are going to cancel out. So we've got 1.74 times 10 to the minus 5 multiplied by the concentration of the acid, which is going to be 2.32 times 10 to the minus 3, divided by the total volume, and the total volume would be 25 plus 8, so it'd be 33. And that would have to be in decimeters, so we'd have to times that by 1,000 as well. Okay, and then we divide that by the concentration of A minus. That's just because they've got to be concentrations. And you can see the 1,000 over 33 would cancel out. So that gives us a hydrogen ion concentration of 2.40 times 10 to the minus 5. So the pH would be equal to 4.62. And we know that the acid is still in excess, and it's a weak acid, so that's a sensible concentration for the pH to be. In terms of marks for this bit, you would get 1 mark for working out the hydroxide ions, another mark for working out the moles of the salt formed, another one for working out how much acid is left after neutralisation, another mark for being able to rearrange this, a mark for working out the hydrogen ion concentration, and a mark for working out the pH. So this section's out of 6. Okay, the final part. 40 centimetres cubed of potassium hydroxide have been added. Well, that's well in excess of the original volume of acid. And as the concentration of the acid was weaker than the hydroxide, we can assume that all of the acid has been neutralised. So this one, we're going to end up with an excess of hydroxide ions. So the first thing I'm going to do is I'm going to work out the moles of hydroxide ions. So it's 40 times 0.20 divided by 1,000, which is 8.4 times 10 to the minus 3. After neutralisation, the moles of hydroxide ions are going to be what we started with minus the moles of acid. Now we worked out the moles of acid earlier on, so we can use that same value. So that gives us an excess of 4.4 times 10 to the minus 3. Okay. I need to convert that into a concentration. So it's going to be the moles divided by the total volume, which is 40 plus 25. So that's 65 times 1,000. And that gives me a concentration of 0.0677. Once I've got the hydroxide ion concentration, I can use Kw. And we know this is taking place at 25 degrees C, so Kw has its usual value of 1 times 10 to the minus 14. And we're going to divide that by the concentration of hydroxide ions that we've just worked out, which gives us a hydrogen ion concentration of 1.477 times 10 to the minus 13. We can work out the pH in the usual way. And that comes in at 12.83. Again, remembering to 2 decimal places, that seems reasonable for a strong alkali. So if we have a look going through here, This one is a maximum of 5. The previous bit was a maximum of 5 as well. I think I'd allow a couple of extra, so you've got a maximum of 15. So for this one, there is 1 mark available for the final pH. There is 1 mark available for the hydrogen ion concentration. There's 1 mark available for working out the concentration of the hydroxide ions. Another one for working out the total volume. Another one for getting the moles of hydroxide in excess. And 1 there for working out the moles of hydroxide. So it's going to be a maximum of 15 for the whole question. It does say if you've missed out a volume, you can only get a maximum of 4. So the first bit of the test was out of 33, and the last bit of the test was out of 15. So the test itself came to a total of 48. If you've gone through this and you still have questions, please bring it along to the workshop or come and see me in class.